After watching the manufacturing process of the world's three major aero engines, one finally understands why the US, UK, and France have become the undisputed overlords behind civil aviation aircraft. Engines, regarded as the heart of an airplane and praised as the flower of industry, take decades, sometimes even a century, to independently research and develop. GE in the US and Rolls-Royce in the UK already dominate more than 80% of the global market. Even China's Comac C919 still relies on an engine provided by GE. So today, let's take a look at how they firmly control the lifeline of aviation engines, and how China is trying to break this deadlock. If the aero engine is the jewel of industry, then the blade is the crown atop it. Manufacturing begins with rough cutting by water jet, followed by 5-axis precision machining. According to engineers, to extend blade life, they use advanced heat-treated superalloys and then employ X-ray and fluorescent inspections, measuring each blade in 5 rounds, reducing error to within 1,000th, in some cases achieving 0 defects. In the global civil aviation engine market, the US and UK dominate. GE holds 40% of market share, Rolls-Royce 22%, and Pratt & Whitney, a Raytheon subsidiary, ranks third. The remaining companies are essentially subsidiaries or derivatives of these giants. For example, the C919's engine is a joint venture between GE and France's Safran, and a single set accounts for 30% of the aircraft's cost. Next, as the compressor disc is slowly connected to the combustion chamber, you can already see the basic structure of the compressor. The front fan disc is installed upside down to the ground to make it easier to insert the turbine disc carrying the turbine blades. The green turbine shaft in the middle connects through the central bore to the compressor at the front, so the turbine blades can capture thermal energy from gases and convert it into mechanical energy. In simple terms, the shaft draws in and compresses air, channels it into the core for further compression, while the bypass air, about 80% of the airflow, is expelled to produce massive thrust. After tightening screws spaced just 1 centimeter apart, the fan module is installed. Although the turbine disc may not look large, once rotating, it must withstand hundreds of tons of centrifugal load, equivalent to hanging the weight of a train. During hoisting, the 10-person team cannot step away for even a moment. Only when the fan and compressor modules are installed in place can the engine be rotated horizontally. To continue the assembly, the outer casing must be removed for internal installation and alignment. And the challenge isn't just ice crystals, but also liquid water. Any engine aiming for international skies must endure these brutal hours-long tests. While many nations can assemble engines, the real hurdles are metallurgy, fatigue resistance, and decades of expertise, making shortcuts impossible. Now back to China's aviation heart. The C919 still relies on imported cores, and export bans have slowed progress. Yet this doesn't mean China is behind. No airliner is built by a single country. Boeing and Airbus also rely on global supply chains. Comac designs and integrates the C919, but 40% of key parts come from abroad. So is it truly domestic? In reality, global cooperation and innovation go hand in hand. In 2018, China's first CJ1000A ignition test succeeded, and in 2023, it powered a C919 test flight. The plan: engines ready by 2025 and commercial deliveries by 2026 to 2027. But to win trust, China's engines must meet, or surpass, Western standards, an unprecedented challenge. With assembly complete, the engines enter the flight test stage. First, an A350 is towed into the test chamber. After removing the tow bar and starting the equipment, parameters are monitored. Once everything is qualified and data recorded, remote reporting to the control tower is done. Finally, let's look at a Rolls-Royce 3D animation for a 1-sentence explanation of how a jet engine works. The engine burns fuel and expels jets to create thrust, pushing the airplane forward. The wings then cut through the air, forming a pressure difference above and below, generating lift. Balance between thrust and lift allows flight, a perfect demonstration of Newtonian mechanics and fluid dynamics.